Hi, my name is Nikhil and I'm a student of Chitkara University, and this presentation is part of my 9.3D task. So in this video I will explain you that how you can implement the hack CPU. So the hack CPU is based on the von Neumann architecture, which consists of CPU, ROM and RAM. This is the design of hack CPU. This is the basic info. Components in the hack CPU, there are a very small number of components. Registers: A register, D register, program counter, M register, and ALU and control unit. And this is the interface of hack CPU. So there are 3 input pins and 4 output pins. Now remember this 16-bit instruction code we'll use later. So this is the code. I will explain you line by line. So in the first 3 lines there are instructions, input. So first one is INM, second one is instruction, and third one is reset pin. So the input memory input is used to receive the value of the memory location being accessed by the CPU. So basically this refers to as M in the code. And then M is defined as the content of the memory location at the address stored in the A register. Okay, so now second pin is instruction. So this is a 16-bit instruction which will our hack CPU will use to execute this instruction. And the third pin is reset pin. So this pin will decide if restart the current program or continue with the executing the current program. So second we have output pins. So first output pin is out M. So this output M is a 16-bit value that is the result of an ALU operation performed by ALU. Second we have write M. So this is a 1-bit value that indicates whether M register should be returned to with no value output, or if write M is 1, then M register is updated with the value of output M, and if write M is 0, then it will be retain its current value. Third we have address M. So the address output is 15-bit that specify the address of the memory address of in the RAM. So M register means memory register. Fourth we have program counter. So program counter is a 15-bit value that specify the address of the next instruction to be fetched from the instruction memory or ROM. Next we have parts. So in the first part we have the node component with inputs instruction 15 and output A instruction. So this bit is used to indicate whether the instruction is A instruction or C instruction. Next we have NOT gate. So this component is also used to indicate whether the instruction is C instruction or an A instruction. So if the value of A instruction is 0, then the instruction is a C instruction. I will tell you with this one. So basically if opcode is 1, then this means this instruction is C instruction, and if opcode is 0, then this instruction is an A instruction, and in A instruction there is only address. So left 15-bit will decide the address. So next we have AND gate. So this component is used to control the selection of the input to the next mux component, and in the mux component this will decide if what do we need to put into the A register. Is it an instruction or ALU output? So basically if it is an A instruction, means from here we will get 1. If we will get 1, then this will put ALU output. If it is an 0, means it is an A instruction, then put the instruction into the A register. So basically if it is an C instruction, then put the ALU output in the A register. Next we have OR gate. So this component is used to control the loading of the A register. In the next we have A register. So this is a built-in chip. So if this output is 1, then it will load the A register input to the output, A output. I mean, this will load the value to the A register. Otherwise it will retain its current value. Next we have mux 16. So if instruction 12 is 1, then B will be output set as a output, AM output, and if it is 0, then A output will be equal to AM output. And if we see our 16-bit instruction decode, then this pin is that instruction 12. We will use it in our ALU. So next we have AND gate. So again this AND gate is used to control the loading of the D register. So this D register is also a built-in chip, so it will load the ALU output to the D register if load D is 1. Next we have ALU. So this ALU, in this ALU there are 6 input pins, which will be instruction 11, instruction 10, instruction 9, and these are 6 control bits. As you can see here, C1, C2, C3, C4, C5, C6. And the inputs are X input is D output and Y input is AM output. Next we have OR gate. So in first OR's component sets all of its output to the value of A out. Next we have OR 16. So this will set all of its output to the value of ALU output. And also the 15-bit will always be here. 15-bit will always be 0 because that's the opcode, and for A instruction opcode is always 0. Next we have AND gate, and in this component so this component is used to control the writing of the M register. So if this is an instruction and instruction 3 is also true, then this will write here. And I will let you just a second. So we have basically 3 destination bits, D1, D2, D3, and here D1 is equals to A register, D2 is for D register, and similarly D3 is for M register. So it's like instruction 0, instruction 1, instruction 2, instruction 3. So there's an instruction 3. This is an instruction 3 for M. Next we have instruction 1, instruction 2, and these are the jump pins actually. So basically we have 3 jump bits. This one is 0, 1, 2. So this is 1, 2, and 0 will be jump greater than. So first AND gate is used to control the execution of jump if it is equal to the instruction, if it is an equal or JEQ instruction. Next AND gate is used if jump is less than. Next OR gate, and this output of this OR gate is used if one output of this component is 1 if either of its input is 1, and 0 if both of its input are 0. Okay. Next we have a NOT gate. So NOT gate is used to negate the value of 0 or negative. Next we have AND component, and in this AND component is used to control the execution of jump is if greater than instruction. Next we have OR gate, and this OR gate is used to control the execution of the jump if less than or equal instruction. Basically we have total 8 jump instructions. Next we have OR gate. So the output of this component is used to determine whether to jump to the address specified in the A register or not. Next we have AND gate, and this output of this component is used to control the loading of the program counter. Next we have NOT gate. So this is used to negate the value of the PC load. Next we have at the last we have a program counter. So the program counter is just like set the value. The PC output is used to send the address of the next instruction to the instruction register, which need to be fetched. Thank you. So these are the differences of this presentation, and thank you.